Alright, this is AP Calculus BC Lesson 1-3. Today's date is Tuesday, February 4th, 2020. Recording it late at night to make sure that this is ready for the day of. Our objective today is to convert from parametric and polar form to Cartesian form to find the shape of the graph. So I'm going to be teaching you can kind of take a peek ahead from parametric to Cartesian, and Cartesian is your normal x, y coordinates, and then how to get from polar to parametric. So if I gave you something in polar, eventually you'd have to go polar to parametric, and then from parametric to Cartesian. And again, the whole goal is to figure out what type of shape are we dealing with. A lot of the questions that you might encounter will just ask you, what is the shape of this guy? And then you'll have to do a bunch of math to figure out what's going on. So it is very helpful to memorize the types of graphs. Lines are of the form mx plus b, y equals mx plus b. And yes, it's a line. We've seen it before. Parabola, y equals ax squared plus bx plus c. We've seen that it can be concave up or it can be concave down as well. We have a hyperbola. The main difference between the hyperbola and the ellipse is one is a minus sign and one is a plus sign. So whenever I have a minus sign, I have two different directions. It's kind of like if I split up the ellipse and then rotated these around, I would get the hyperbola. And notice here the difference between the ellipse and the circle is that the ellipse, I can have different dimensions for the denominators. So a squared, b squared are different, and then a squared and a squared, they're the same number. Therefore, we'll have a circle. So yeah, make sure we have that list memorized. Let's try to do some math here. So let's try converting from a parametric to a Cartesian function. So I'm going to be using this term a bit. It's called eliminating the parameter. Essentially, whenever I'm saying eliminating the parameter, I just am trying to say you're getting rid of the t variable. Because remember that a parametric function looks something like this, where we have x is equal to something, y is equal to something, and we want to get rid of that t, and then we're left with x and y, which is exactly what we want. We want this normal. All of these are in your Cartesian form, where I have y and x. Y and x. There's no t's, there's no extra thetas or anything like that. There's no r's. So how are we going to do that? So this is the order that you should always do it in. Step 1, always try to look for subtraction, then use trig identities, and if those two failed, then use substitution, because that one will always work. So the first one to check is subtraction, and this is kind of like, maybe I should put elimination up here. Elimination. That might be a more apt name for it, because you're just trying to eliminate that t variable. And that's only if you have the same t in both equations. So in this example, I have a t squared and a t squared, so this is a good way of doing it. If I had a t cubed here or something, then it wouldn't work. Although you could probably still use it. If I had 2t squared, I just have to subtract 2 of these. Let's show you the math. So how do we get rid of one? Well, I can just do x minus y, or y minus x. It doesn't really matter. So I'm going to say x minus y. If I do x minus y, well, here's x. So I'm going to put this in parentheses just to show my work. This is t squared plus 3, and I'm going to subtract my y. My y is t squared plus 6. So after subtracting, I get x minus y is equal to, I want to just distribute this negative, so it's going to be t squared plus 3 minus t squared, and then distributing the negative, it should be a minus 6 now. And notice, I guess I should change colors for each line to make the notes pop out a little bit. Grab the y. Give me a sec here to fix this. Alright, looks better. And then from here, you'll notice that the t squares are going to cancel each other out, and I'm left with x minus y is equal to 3 minus 6 is negative 3. And then from there, I'm going to do two different things. I'm going to add y to both sides, and I'm also going to, I guess I'll just do one step at a time. I have plenty of room. When I do that, I'm left with x is equal to negative 3 plus y, and finally I'm going to add 3 both sides, plus 3, and I'm left with y is equal to x plus 3. And I didn't really ask the question very well, but I should be asking every single one of these examples, what is the shape? That is our whole goal today. What is the shape of this equation? And the answer, if I look down here, it's x plus 3 is equal to y. It looks very, very very similar to this standard function for a line. mx plus b, it's 1x plus 3. So the answer here is this is a line. I don't know why I'm doing quotes. Yeah, I'll just say it's a line and box it. All right, what happens if I can't use substitution? Then I have to go to the next step of using a trig identity, specifically using this identity right here. It's the Pythagorean identity. And this will only work if one equation has a sign and the other equation has a cosine. So one of them has a sine, one of them has a cosine. And you'll notice a similar, or something that's kind of interesting, which is whenever we're doing polar to parametric function, we're always going to have a cosine, we're always going to have a sine, which means you're going to be using this rule pretty heavily whenever you're converting from polar to parametric and then from parametric to Cartesian using the trig identity. I think I've said too much. Let's go ahead and jump into this problem. So I want to kind of set up this problem. I'm looking for sine squared and cosine squared. So I'm gonna build this function isolating the sine, isolating this cosine. So if I isolate the sine, I'm really dividing both sides by 5. So I have x over 5 is equal to sine of t. And I'll do this in a different color to make it stand out a little bit. Y divided by 4 is equal to cosine of t. Again, I'm trying to find sine squared. So what I need to do to this blue equation is I need to square both sides. So after I square both sides, I'm left with x over 5. The left-hand side is squared, and now the right-hand side is squared. That's how we write a square. Like normally you'd think, oh, you do sine of t squared. Yeah, if that square is there, is on the right hand side, it's technically on the inside to be formal about it. So it should be sine squared of t. I'm going to make my t slightly curly to make it stand out from plus signs. And then the same thing for the yellow. I'm just going to square both sides. So I'm going to get y over 4 quantity squared is equal to cosine squared of t. Okay, well, I've built my function. I have a sine squared, I have a cosine squared. Let's plug these into this Pythagorean identity. So right underneath this, sine squared, this sine squared right here is this sine squared, which means it's really x over 5 squared. So this is going to be x over 5 quantity squared plus, and then I'm going to sub in this for cosine squared. This is cosine squared, which means I'm really plugging in y over 4 squared. So this is going to be y over 4 quantity squared, and that's equal to 1. I've plugged into the Pythagorean identity. And it's pretty clear what's going on here. I can just reduce it one more step. This is x squared over 25 plus y squared over 16 is equal to 1. And we can see, oh yeah, so when it's a plus sign, that's an ellipse. If we come back up here, I have a plus sign in between them, and they're different numbers in this case, then it's an ellipse. If these were the same number, it would have been a circle like that. But the answer down here is this is an ellipse. Let's write it down. Number 3. So only do this if you've tried step 1 and step 2 and neither of them work, or you maybe didn't try it, but you recognized it didn't have a sine, it didn't have a cosine, this variable wasn't the same here and here. So if you notice those things, then you do have to do step 3. It is a little bit more tedious, which is why we do it last, but it does always work. So substitution. The way that substitution works is I'm going to isolate for t, so I'll put it over here. Isolate t, and then we'll plug it in. So I can isolate for that t. No, that's going to generate a square root. Let's isolate for this t. So I'm going to subtract 7 from both sides. So that's going to leave me with x minus 7 is equal to t. All right, this equation over here is still the same. It's still y is equal to t squared. I haven't touched that equation. I'll just keep copying it down. Okay, so now I'm saying that this t is x minus 7, which means this t is also x minus 7. So here comes the substitution. I'm now going to say y is equal to this thing quantity squared, because I'm copying on this squared, and on the inside of this is this blue x minus 7, x minus 7, and I'm basically done. I can't tell what function this is yet. It is in Cartesian form, so I'm going to go ahead and square this and see what happens. Again, remember the trick for squaring. There's 3 steps, right? 1, 2, 3 for squaring. This is our shortcut for squaring, which is to square the first. That's a bad U. Square the first. Then double the product. I'm just going to write product like that, and then square the last. So that's what I'm going to do over here. So this is now going to read y is equal to square the first, x squared. Double the product. So what is the product of negative 7 and x? Well, that's negative 7x. Then double that. Negative 7x times 2 is negative 14x. Negative 14x. And finally, square the last. Negative 7 squared is positive 49. And this is much clearer now. This is a quadratic because it's x squared minus 14x plus 49. That looks very similar to this form right here. So we're dealing with a parabola. Oops. And Shift C. So the answer here is a parabola. All right. So that's kind of a giant section on how to get from parametric to Cartesian. And then very quickly, polar to parametric. These are the easiest ones. But then going again from parametric to Cartesian, I'll write this down. So if you have polar, you go to parametric and then I'll say then to Cartesian. If I ask that of you, but I'm not going to do that today on the homework, but you might eventually be asked to do that. So it's pretty straightforward as long as you memorize your formulas. We've talked about where these come from. I don't want to go into depth in this video on where they come from because I've talked about it twice in pre-calculus and in algebra 2. If you do have questions, just ask me later. Cosine goes with x, sine goes with y, and you always are going to multiply by your modulus, by your length, your radius. So here's an equation that's in polar form. If I graph that, you'd see some cool flowery things happen. So in order to turn this into parametric form, remember parametric form says x is equal to something, y is equal to something with t's in it. Let me move this y a little bit over to the right because I need some room. And all I have to do is write out my formula. So first, x is equal to r. Well, what is r? R is this entire thing, so I'm just going to copy down in parentheses 1 plus sine of 2 theta. Okay, I just copy down r, and then I say times cosine of theta, times, and I can have enough room, move this a little bit more, times cosine of theta. Done. All right, let's do this in a different color to make it pop out a little bit more, using the same exact formula. So I'm going to write it down again. Let's get rid of this circle up here too. Oh no, I just want to grab, there you go. Now I'm going to do r again, and then I'm going to multiply that by sine of theta. It's essentially the same thing, but instead of a cosine, I'm going to change that to a sine. So it's going to be 1 plus sine of theta times sine of theta. And done. That's all I have to do. So those problems on the homework will go really, really quick. That concludes notes 1-3 for AP Calculus BC.